Max Tegmark once sat down with the plane geometry of space and worked out the distance to a person who is you, atom for atom, lying the way you are lying now, holding this exact thought at this exact moment. He did not do it as a flight of fancy or as a thought experiment meant only to unsettle. He did it the way you might work out how far it is to a town you will never visit, starting from a few measurements anyone can check and letting the arithmetic carry him the rest of the way. And the number he arrived at is a real number, large past all telling but real, the kind of figure you could in principle write down if you had paper enough and years enough to spare. Not a soul, and not a metaphor for the roads you did not take. A physical person, built from the same kind of atoms as you, resting in the same posture, with the same faint weight settling into the same shoulder, with your memories folded the same way inside a brain arranged the same way, somewhere out in space that our best measurements suggest may simply keep going. That person is not a story anyone invented, for comfort or for fright. If a few ordinary things about the universe turn out to be true, and every measurement we have says they are, then that person is a consequence of arithmetic, the same arithmetic you learned as a child, carried out across a cosmos far larger than the small lit part of it we are able to see. That lit part is already almost past imagining. The light reaching your eyes tonight from the faintest and farthest things has been traveling toward you for something close to 14 billion years, since long before there was an earth or a sun for it to fall on, and the great sphere it traces out around us is what astronomers call the observable universe. The whole quiet turn of tonight, the thing that lets arithmetic become company, is that this staggering sphere is very probably not the whole of what exists, but only the part that happens to lie near enough for its light to have reached us yet. Tegmark even put a number on how far away the nearest one should be, and he was careful, when he did it, to be conservative about the figure, to lean toward caution rather than toward drama. Even so, the number comes out quiet and absurd at the same time. Written out in meters, it would be a one trailed by so many zeros that the zeros themselves run past anything the mind can hold. A figure close to 10 raised to a power that is itself 10 raised to the 29th. You will never walk that far. No traveler ever could. Light itself, the fastest thing there is, will never finish the trip, not across the whole long lifetime of the universe. And yet, and this is the part worth keeping, the distance is not infinity. It ends. Somewhere out along it, at a place you could name if only you could count that high, the room you are lying in begins again. What makes it stranger still and gentler is that none of this leans on anything exotic. There are no extra dimensions hidden inside the argument, no unseen powers, no science fiction of any kind waiting in the wings. It follows from 3 unremarkable measurements, the sort a patient person with good instruments could go and check. How flat space is, how evenly matter is scattered through it, and how far it seems to reach before our sight gives out. We will take those 3 in turn tonight, slowly, one after another, and watch the far person appear at the end of them, the way an answer appears at the foot of a long column of sums. For now it is enough to know that the road out toward them is short and ordinary, even if the place it finally arrives is neither. Here is the gentle strangeness of it, the thing that turns a cold equation warm. They think they are the only ones. Wherever they are, in a room you will never reach and never see, they are having the very thought you are having now, that there is just one of them, one life being lived out in one body, One small warm circle of lamplight in all that surrounding dark. They are as certain of it as you are, and they are wrong about it in exactly the same quiet way that you have always, without ever once noticing, been wrong about it too. Somewhere, the same lamp is on. Picture it for a moment before we begin, since the whole night will keep returning to it. A single warm lamp burning in a dark window, and then another window just beside it, with the same lamp lit inside, and another past that one, and another, until the windows multiply into a city with no ground beneath it, and no sky above it, an endless still field of identical lights stretching away in every direction farther than looking can follow. Each light is a version of this room. Each one holds a version of you, settled in for the night, certain the light is theirs and theirs alone. You can never walk to any of them. Their light will never reach your window, and yours will never reach theirs, because the distance between you is the kind that light itself runs out of time to cross. And still the lamps are on, all of them, burning quietly and unreachably across a dark that has no floor. We will keep coming back to that far lamp tonight, at every turn of the argument, because you are one of them, a small light among an uncountable many, and one that is, soon and softly, going out. Tonight, we're going to explore how 3 unremarkable facts about the shape of space lead, step by step, to that first far lamp, and then to the second one, and the millionth, until the word you slowly stops meaning only one person. We will widen the idea 4 times before the night is through, each time from a greater distance than the last, and each time, if it goes the way it should, it will feel a little less like a fright and a little more like company. There is nothing here you need to solve, and nothing you need to keep hold of. If you would like the channel to find the next person lying awake wondering these same quiet things, you can follow along, and that is the whole of the asking. Otherwise, let your eyes close whenever they want to. The lamp will still be on when you get there. So let us begin where the whole idea begins, which is not with infinity at all, but with a triangle. Draw a triangle on a flat sheet of paper, and its 3 angles always add up to the same total, the half turn we all learn to expect in school. Draw that same triangle across the surface of the earth, letting its sides follow the curve of the ground, and the angles quietly add up to a little more, because the surface beneath them is bowed gently outward. Draw it instead across a shape that curves the other way, something saddle-shaped that falls away on 2 sides at once, and the angles come up a little short. The surface leaves its fingerprint inside the triangle, and that means, if you are patient and careful enough with your measuring, you can learn the shape of a surface without ever stepping outside it to look. That last idea is worth pausing on, because it is older and more human than it sounds, and someone once used it to measure the whole earth without ever leaving the ground. Around 200 years before the Common Era, a Greek scholar named Eratosthenes, living in Alexandria in Egypt, heard that on the first day of summer, in a town to the south called Syene, near what is now Aswan, the noon sun stood so perfectly overhead that it lit the bottom of a deep well and threw no shadow at all. On that same day, at that same hour, in Alexandria to the north, a tall column did cast a shadow, and from the length of it, Eratosthenes could tell that the sun there stood about 7 degrees off from straight overhead, roughly a 50th of a full circle. The sun's rays arrived very nearly parallel, so if the ground between the towns had been flat, the 2 places would have seen the same sun at the same angle. They did not. The only thing that could tip the one reading away from the other was the curve of the earth itself, bending its surface between the two towns. Knowing that the cities lay about 5,000 stadia apart, and that this span accounted for 1/50th of the whole, he multiplied it out and arrived at the circumference of the earth. He never once climbed above it. He read the shape of the whole world from inside it, out of nothing more than sunlight, a shadow, and the small angle between them. Space can be curved in just the way the Earth's surface is, only in one more dimension than we can easily hold in our mind. Not the things resting in space, the stars and the dust, and the long, dark distances between them, but space itself, the fabric that all of it sits within, and that light must cross to reach us. It can bow outward, so that great cosmic triangles come out full, and their angles sum to more than the flat value. It can fall away, so that they come out lean and sum to less. Or it can lie flat, and close at exactly the total Eratosthenes would have expected on a sheet of paper. And remarkably, we have found a way to draw a triangle wide enough to tell which of those it is, a triangle whose far corners reach back almost to the beginning of everything. The trick is to use the oldest light there is. In the first few 100,000 years after the beginning, the universe was far too hot and too crowded for light to travel freely. It was a bright fog, a plasma so dense that a beam could not cross a room in it without being scattered again, the way a headlamp cannot reach far into thick mist. Then, about 380,000 years in, the whole of space had cooled to somewhere near 3,000 degrees, cool enough at last for the loose particles to settle into the first calm atoms, and in that moment the fog cleared. Light that had been trapped and rattling since the very start was suddenly free to fly in a straight line, and much of it has been flying ever since, cooling and stretching all the way. It reaches us now from every direction at once, drawn out by the long journey into a faint whisper of microwaves, and we call it the cosmic microwave background. We did not go looking for it, at least not the two men who first heard it. In the middle of the 1960s, in Holmdel, New Jersey, Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Labs, trying to track down a faint, persistent hiss that fouled their measurements. The hiss would not go away. It came from every part of the sky, day and night, in every season of the year, no matter where they aimed the horn. They checked the instrument. They checked the wiring. They even cleared out a pair of pigeons that had roosted inside the antenna and left it, as Penzias delicately put it, in a less than clean condition, and they scrubbed the horn out, and still the hiss remained, steady and everywhere. What they were hearing, it slowly became clear, was the cooled glow of the young universe itself, the leftover warmth of the moment the fog first cleared, arriving as a soft, even murmur from all directions at once. The predictions of the day had said that such a glow, if it existed at all, should be faint and cold, somewhere below 40 degrees above absolute zero, and what the two of them found sat at only about 3 degrees above that floor. It was 1965, and their accidental hiss quietly settled one of the largest questions there is, whether the universe had a hot and dense beginning. It had. Years later, the discovery would carry them a Nobel Prize, but on the day itself, it was mostly two puzzled engineers and a very clean antenna. Later, in 1989, NASA launched a satellite called COBE to study that same glow from above the muffling blanket of our atmosphere, with an eye to measuring it more precisely than any antenna on the ground ever could. The readings that came back, worked over by John Mather and George Smoot, among others, matched the predictions so exactly, tracing the smooth curve that a glowing body of a single temperature is supposed to trace, that a hall full of astronomers is said to have broken into applause at the sight of the graph. The temperature of that ancient light, measured against the cold of space, came out to about 2.7 degrees above absolute zero. Just those few degrees of warmth spread with astonishing evenness across the entire sky. And that evenness matters nearly as much as the warmth, because when Kobe turned from one part of the sky to another, the temperature barely shifted at all, holding the same to a remarkably fine fraction in every direction it looked. And here is the part that turns that faint, even glow into a triangle. The oldest light is not perfectly smooth. Frozen into it is a pattern of very slight ripples, places where the early universe was a whisker warmer or a whisker cooler than its surroundings. And the typical size of one of those patches is a length that theory can predict from first principles. We know, in other words, roughly how large one of those warm or cool spots ought truly to be. We can also measure how large it appears to us in the sky, the angle it spans from where we sit. The true size and the apparent size are two corners of an enormous cosmic triangle, and the way the one maps onto the other reveals whether the light traveled to us across flat space or across space that curved along the road. Curved space would have acted like a lens, magnifying the patches or shrinking them, bending the angles away from what flat space would give. Flat space would leave them true. When cosmologists finally measured this, combining the exquisitely detailed maps of that ancient light with the way galaxies spread in great patterns across the sky, the answer came back flat. Flat to within about 0.4%, as near to perfectly flat as our instruments can currently tell. The Great Triangle closes at very nearly the total it would close at on a flat sheet of paper, drawn across the whole width of the observable universe. Now hold what that means slowly, because everything tonight rests upon it. A space that is flat, and that does not fold back on itself the way the surface of a globe eventually curves around and returns to where it started, has no far side. It does not bend around to meet itself. It simply continues in every direction, with no natural place to stop and no wall to run into. We cannot prove there is no edge somewhere far past our reach, and a few careful people have wondered whether space might yet be folded, on the very largest scales, into some subtle shape we have not managed to catch. But the reading we have, taken plainly and at face value, is of a universe that keeps going, which brings us, of all places, back to the mapmakers. For most of human history, the people who drew maps drew the edges of a world they had never sailed to. They inked a coastline where the last reliable report gave out, and past it they left open water, sea monsters, warnings, and honest guesswork, and the map looked finished only because the parchment ended. But the edge of the parchment was never the edge of the ocean. It was the edge of what anyone had yet seen. The sea went on past it exactly as it had before, wholly indifferent to the fact that no one had drawn it. The boundary we speak of in astronomy is that same kind of edge. We talk about an observable universe, a great sphere with us sitting at its center, and it is easy to hear that phrase as a wall where space itself runs out. It is nothing of the sort. It is simply the distance that light has had time to travel since the beginning. And we can say, at least closely, how long that has been. The whole of it has been expanding for something on the order of 14 billion years, a figure astronomers reach in a satisfyingly plain way, by measuring how quickly distant galaxies are drawing away from us, and then, in effect, running the expansion backward to ask how long ago all of it would have been gathered together in one place. Careful work has sharpened that estimate to close to 13.8 billion years. So the observable universe is simply the sphere from which light has had those 13 or 14 billion years to reach us, and not one moment more. Anything whose light would need longer than the universe has so far existed has plainly not arrived, and sits for now quietly below our horizon. And there is a deeper reason than distance alone, that some of that far light will never reach us at all. In the closing years of the 20th century, two teams of astronomers set out to measure how quickly the expansion was slowing down, using a particular kind of exploding star, a type Ia supernova, which flares so predictably bright that its true brightness is known, so that how faint it appears to us reveals how far away it must actually be. They fully expected to find the expansion gradually breaking under the gravity of all the matter in the cosmos. Instead, they found the exact opposite. The most distant supernovae came in fainter, and therefore farther, than any slowing universe could account for. The expansion is not breaking at all. It is speeding up, carried along by something we have named, for want of any real understanding of it, dark energy, and the finding was startling enough to be awarded a Nobel Prize in the year 2011. What that acceleration means for tonight is quiet but final. Space is not only vast, it is bearing its most distant contents away from us faster and faster, so that light setting out now from regions beyond a certain distance will never, however long anyone waits, close the growing gap between us. The far copies are not merely far away. They are being carried further with every passing moment, sealed off behind a horizon that is, in the truest sense, permanent, which only deepens the gentle strangeness of the far lamp. You have not simply failed to walk to it yet. The road itself is lengthening faster than any walking could ever hope to cross it. So the horizon marks the edge of what could possibly have arrived at our eyes, not the edge of what is actually out there. It is a horizon of information, the coastline where our reports stop, and nothing more. And what lies past it, everything we can see strongly suggests, is simply more of the same. Everywhere we have looked, in every direction, the universe wears the same broad face. Count the galaxies in one patch of the sky, and then in another far across from it, and the tallies come out much the same. Look near and look far, and allowing for the slow changes that time brings, the picture holds steady, the same gentle scattering of galaxies, the same great web of them strung across the dark, the same quiet machinery building, the same kinds of stars under the same rules. Astronomers gave this evenness a name, the cosmological principle, the working assumption that the universe is much the same everywhere and looks much the same in every direction. And it is not merely an assumption of convenience, it is what the counts and the surveys actually show. There is no reason written anywhere to think the pattern suddenly changes just because it has crossed the line past which our light cannot reach. The most natural reading of everything in front of us is that the parchment ends and the ocean does not. And if that is so, then the first far lamp is already lit, because a universe that keeps going is a universe with room enough for the rest of tonight. But the room, on its own, changes nothing at all. Endless space, empty of consequence, would be only a very large and very quiet nowhere. So the next question is the gentler one that turns all that emptiness into another version of you. And it is really, when you follow it down, a question about counting. Before we count, there is one honest thing we have been quietly taking for granted all night, and it is worth a slow pause, because the whole argument leans its weight on it. We have been speaking of distance as though it were a simple thing. The distance to your twin, the distance to the horizon, a number Tegmark could write down. But stop and ask how anyone measures the distance to something they can never visit, never touch, never send anything to, and never hear back from. It is the very question the far lamp asks. How far away is a light you can only see? For most of human history there was no answer at all, only guesses, and the answer we do have was built slowly, one careful rung at a time, by people who never left the ground. Begin with the trouble itself, because it is a trouble you already know in your body. Picture a single light in the dark, far off. A firefly close by your hand, an oncoming motorcycle somewhere down the road, the porch light of a house much farther along. From the light alone, from nothing but how bright it looks to you, you cannot say how far away it is. A dim glow might be a faint thing close by, or a blazing thing very far off, and the two can look exactly the same to the eye. This is the whole difficulty of measuring the sky, set out in miniature. A star that looks faint might be a small, cool star near at hand, or a brilliant giant at an enormous remove, and until you can somehow learn its true brightness, its real output, you cannot turn how dim it looks into how far away it is. There is a simple rule underneath this, worth holding on to, because the rest of the night quietly uses it. Brightness falls off with the square of distance. Move a light twice as far away, and it looks not half as bright, but a quarter as bright. 3 times as far, and it looks a ninth as bright. So if you ever do know a light's true output, its faintness tells you its distance exactly. The problem was never the arithmetic. The problem was always knowing the true brightness to begin with. The way out was a ladder, and like any ladder, each rung rests on the one below it. The lowest rung is our own solar system, and here the trick is almost brutally direct. We send out a pulse of radar, a beam of radio waves, and we time how long it takes to travel to a planet and bounce back to us. Since the beam travels at the speed of light, which we know with great precision, the round trip gives the distance straight away, the way a bat or a ship's sonar finds a wall by its echo. Bouncing radar off the nearer planets in this way, astronomers pin down the true scale of the solar system, and in particular the average distance from the Earth to the Sun, a length so useful they made it a unit of its own, the astronomical unit. That is the firm ground the whole ladder stands on, a distance measured, not assumed. The next rung reaches out to the nearest stars, and it uses a trick you can perform right now without moving from your bed. Hold up one finger at arm's length and look at it with only your left eye, then only your right. The finger jumps against the far wall behind it, back and forth, as you switch eyes, because your two eyes look at it from slightly different places. That small jump is called parallax, and the closer the finger, the larger the jump. Surveyors have used this for centuries to measure the distance to a far tree or a mountain they cannot reach, by observing it from the two ends of a known baseline and watching how much it shifts. Astronomers do exactly the same with the stars, and their two vantage points are the Earth itself, at opposite ends of its long journey around the Sun, half a year apart. A nearby star, seen against the distant ones behind it, shifts by the faintest amount over those 6 months, and from the size of that shift, its distance falls out by plane geometry. The shifts are cruelly small. The first person to catch one and measure it soundly was Friedrich Bessel, who fixed the distance to a star called 61 Cygni in 1838, a feat that had defeated careful observers for a very long time, because the angle he was chasing was smaller than the width of a coin seen from kilometers away. In our own time, spacecraft built to do nothing else have carried this method far past what any ground telescope could manage. A satellite called Hipparcos measured the distances to thousands of stars out to a few hundred light years. Its successor, Gaia, has been charting the positions and distances of very nearly 1 billion stars, to an accuracy of a few millionths of a single arc-second, reaching out across tens of thousands of light years of our own galaxy. That is the second rung, and it climbs a good way, but it does not climb far enough. Parallax runs out long before the other galaxies begin. The third rung is the one that changed everything, and it came from a particular kind of restless star and from a woman patiently reading photographic plates in Massachusetts. Some stars are not steady. They pulse, swelling and shrinking in a slow, regular breath, brightening and dimming as they do, on a cycle as dependable as a clock. 2 families of these pulsing stars turned out to matter enormously, the ones called Cepheids, named for the first of them to be noticed, in the constellation Cepheus, and the fainter ones called Lyrae. In the first years of the 20th century, Henrietta Leavitt, working as a staff member at the Harvard College Observatory, was studying photographs of 2 small companion galaxies to our own, the Magellanic Clouds, and in them she found well over 1,000 variable stars, Cepheids among them. Because all of those stars sat together in the same distant cloud, they were all, near enough, at the same distance from us, and that single fact was the key that unlocked the sky. If 2 of them looked different in brightness, that difference had to be real, a difference in their true output, not a trick of one being nearer than the other. And when Leavitt lined them up, in 1908, she found something beautiful and orderly. The Cepheids that shone with the greater true brightness were precisely the ones that pulsed with the longer, slower period. The rhythm of the star told you its wattage. Time the beat of a Cepheid, and you know how bright it truly is. Know how bright it truly is, and its faintness in your telescope tells you, by that simple square law, exactly how far away it lies. A Cepheid became a kind of lighthouse, with its distance written into its blinking, and there are Cepheids bright enough to be picked out not just in our own galaxy, but in others. Polaris, the star we steer by, is itself one of these gentle pulsars. That gift carried astronomers up onto the 4th rung, out among the other galaxies, and it is where a familiar name enters. In the 1920s, Edwin Hubble found Cepheids in the faint spiral of Andromeda, and in other such spirals, timed their pulsing, read off their true brightness, and so measured their distances. The answer was staggering and settled a long argument at a stroke. Those spirals were not clouds within our own galaxy at all. They were whole separate galaxies, islands of billions of stars, unthinkably far beyond the edge of the Milky Way. And when Hubble then looked at how the light of those galaxies was stretched, reddened by their motion away from us, he found that the farther a galaxy lay, the faster it was receding, which is the discovery that first told us the whole universe is expanding. The stretching of a galaxy's light, its redshift, became a ruler of its own for the greatest distances, and for the very farthest reaches of all, astronomers turned to the brightest reliable beacons they had. Those type Ia supernovae we met earlier, the exploding stars whose true brilliance is known, the same ones that later revealed the expansion speeding up. Each of these top rungs was calibrated by the rung beneath it. The supernovae were checked against the Cepheids, the Cepheids against parallax, the parallax against the radar-measured scale of our own solar system. The whole soaring chain rests, in the end, on an echo bounced off a nearby planet. This is what people mean, though they rarely say it, when they speak so easily of the distance to a far galaxy or the distance to your twin. That word distance, stretched across the cosmos, is not a guess and not a metaphor. It is the top of a ladder that humanity built rung by patient rung, each one tested against the last, reaching from a radar echo in our own neighborhood all the way out to exploding stars near the edge of the visible. And climbing it taught us something quiet that matters for everything still to come. All the way up, at every rung, we found the same kinds of stars burning by the same rules, the same physics holding in the farthest galaxy as in the nearest, which is the deep reason we trust that the universe really is the same sort of place wherever we look. The ladder does not only measure the distances, it confirms, rung by rung, the sameness the whole argument needs. So the far lamp is no longer quite so unreachable as it seemed. We still cannot walk to it, and we never will. But we are no longer helpless before it. We have learned, slowly and honestly, how to stand on the ground and measure how far a light burns, even a light at the very edge of sight. And with distance made into a real and earned thing, a thing with a firm floor under it, we can at last return to the counting we promised, and to the strange arithmetic that turns all this measured room into another you. Start with something small enough to hold in one hand, an ordinary coin. Flip it once and it lands one way, with an even chance it could have landed the other. Flip it 10 times in a row, and you get one particular run of heads and tails, one string out of a modest and perfectly countable set of possible strings. You could, if you were patient, write every one of those possible runs down on a single sheet of paper, or 1,024 of them, and not run out of room. And because that list is finite, if you kept flipping long enough, every run on the page would eventually turn up, and then turn up again, and again, because a finite list met by endless tries leaves nothing out forever. Given enough throws, even the rarest pattern, the one that feels as though it ought never to happen, 10 heads in a solemn row, arrives right on schedule and then keeps arriving. Make the example a little larger, and the point grows teeth. Take an ordinary deck of playing cards, 52 of them, and shuffle it well. The number of possible orders those cards can fall into is not small. It is about 8, followed by 67 more digits, a figure so large that if every person who has ever lived had done nothing but shuffle a deck once every second for the whole history of the universe, we would still have turned up only the faintest sliver of the possible orderings, and almost every shuffle you have ever made in your life was very likely an order that had never once occurred before anywhere and never will again. And yet, for all its vastness, that number is finite. It has a last digit. The orderings run out. Shuffle forever, and every one of them must eventually come around again, because forever is longer than any finite list can hold out against. Now make the coin, or the deck, the size of everything you can see. The region of space inside our horizon, the whole observable universe out to that coastline of light we spoke of, holds a vast but strictly countable amount of matter. If you set out to tally every particle within it, every one of the small pieces that build the atoms that build the stars and the dust and you would arrive at a number somewhere near 1, followed by roughly 118 zeros. It is a staggering figure, more pieces than there are grains of sand on every shore of every ocean you could ever dream of, more than the mind has any true handhold for. But notice the one thing about it that matters most tonight. It is a number. It ends. However far down the page you write it out, there is a last digit waiting at the bottom. And a finite amount of matter, packed into a region of a given size, can be arranged in only a finite number of distinguishable ways. Sit with that quietly, because it is the whole hinge of the night. The count of possible arrangements for a region like ours is a number so enormous that writing it out in full would outrun the paper and the ink and the patience of the one writing it. A number beside which even the count of particles looks almost modest. And yet, exactly like the runs on the coin flipper's page and the orders in the shuffled deck, it is still finite. There is a last arrangement on the list, however impossibly far down the page it sits. The possibilities are beyond counting in any human sense, but they are not beyond counting in the mathematical one. They come eventually to an end. A finite list, laid out across space that does not end, is the shuffled deck all over again, only unthinkably larger. Every arrangement on the list has to occur somewhere out there, because there are endlessly many regions the size of ours scattered through endless space, and only finitely many ways for such a region to be. The regions outnumber the possibilities without any limit at all, so the possibilities cannot help but repeat, not once, but without end. And one of those arrangements, sitting somewhere on that unthinkable list, is precisely this one, this room, this hour. The particular knot of atoms that is your body, resting the way it is resting, holding the very thought it is holding right now. It is on the list, so it is out there, and not a single time, but again and again, past any hope of counting. It is worth being clear about how strong that word must really be. We are not merely saying that your copy might be out there if we happen to get lucky, the way a rare hand of cards rewards a patient player who keeps dealing. We are saying something firmer than luck, a possibility with even the faintest chance above zero. Once it is given endlessly many separate and independent occasions to occur, does not merely probably occur. It occurs with certainty, and having occurred once, it occurs again, and keeps occurring without end, because no finite rarity can hold out against an unlimited supply of chances. Your own arrangement plainly has a chance above zero, since here you are, holding it. Endless space supplies endless chances. What follows from those two plain facts is not luck at all. It is arithmetic, patient and exact. This is where Max Tegmark did something quietly bold. He was not content to say that your copy exists somewhere in the endless dark and leave it as a shrug at infinity. He asked how far away the nearest one ought to be, given how densely these arrangements can be packed into space, and he worked out the figure. It is the same distance we named at the very beginning, that number with more zeros in it than the mind can hold, close to 10 raised to a power, that is itself 10 raised to the 29th, measured in meters, far past anything light will ever cross, and yet we keep remembering, not infinite, a real distance with a real end, along which the room you are lying in begins again. And there is a gentle logic to how those distances scale, one worth resting on for a moment. The smaller the thing you ask to see repeated, the sooner it recurs. Ask only for a copy of yourself, a single person's worth of arrangement, and the nearest one is near, in the strange sense that the word can still carry out here. Ask instead for something far larger, an exact duplicate of the entire observable universe, the whole sphere out to our horizon with every galaxy set in its place, and you must travel very much farther before the pattern comes around again, out to a distance of something like 10, raised to a power that is itself 10 raised to the 115th. The bigger the thing you want matched, the more space you must cross to find it matched. But at every scale, near or unthinkably far, the answer underneath is the same. Given endless room and only finite ways to fill it, the thing repeats. Tegmark called this the first and most modest of his multiverse levels, the least exotic of them all. And modest is the right word, because it asks for nothing strange. No parallel dimensions, no branching realities. Only that space keeps going, as our flat triangle suggests it does, and that it stays on average the same kind of place we already see all around us. And here is where the word you begins, very gently, to come loose. That distant person is not a resemblance of you. Not someone who would merely remind an old friend of you across a crowded room. Every physical fact that is true of you is true of them, right down to the last arrangement of the memories they are certain belong to them alone. Memories of a childhood, a face, a whole life they are just as sure they lived. So ask the question softly, because it turns out to have no cruel answer. Are they you, or are they only identical to you? The philosopher Derek Parfit spent a great part of his life on questions shaped exactly like that one. In his book, Reasons and Persons, published in 1984, he liked to imagine a machine that could scan your body down to the last particle, record the arrangement precisely, and then build a perfect copy of you somewhere far away, atom for atom and memory for memory, while the original was, let us say, quietly taken apart in the scanning. The copy steps out at the far end, remembering having stepped in, feeling in every respect like the same continuous person who first walked into the machine. Is it you? Did you travel, or did you die on the near side and leave behind a stranger who only believes he is you? He pressed the question harder still with one small and unsettling change to the machine. Suppose that one day it scans you as before and builds your perfect copy on the far side. But this time, through some fault, it fails to take the original apart. Now there are simply two of you, both fully continuous with the person who walked in, both remembering the same single life as their own, and suppose the original, left here on the near side, carries an injury from the scanning that will quietly end them within a few days. Which one is really you now? The one here who will soon be gone, or the one walking on for decades wearing all of your memories? Parfit's point was that the question feels desperately urgent, and yet has no clean answer, and that this itself is the lesson worth learning. Perhaps we have been asking the wrong question all along. The thing that actually matters, he came to think, may be the continuity itself, the memories carried forward, the intentions kept, the character held across the years, and that continuity can hold even in the strange cases where our simple idea of a single, countable self quietly comes apart in our hands. Parfit's careful conclusion, reached over many hundreds of patient pages, was that the question may simply have no deep answer, because there may be no deep fact of the matter there to answer it. What we call being one continuous person, he argued, is not a single shining thread running unbroken beneath all your years. It is a continuity of pattern, of memory linking to memory and intention to intention, real and precious in the way a long story is real and thinner, when you look very closely, than it feels from the inside. And a pattern, unlike a soul, is exactly the kind of thing that can, in principle, occur more than once. The striking thing is what Parfit himself made of this. He did not find the conclusion bleak, and he wrote about that plainly. When he came to see his own identity as a matter of pattern and connection rather than a hard, separate self walled off from everyone else, the walls between himself and other people seemed to him to grow thinner, and the prospect of his own death seemed less like the snuffing out of something absolute and more like the fraying of a pattern that had never been quite as separate as he once believed. He described the change as a kind of relief, as though he had been let out of a small dark cell of the self and into the open air. That is worth carrying, because it is the same quiet turn we are making tonight. The far twin only frightens if you are certain you are a single sealed thing. Loosen that certainty even a little, the way Parfit gently did, and the twin stops being a rival for the title of you and becomes something closer to kin. So the twin is not a threat to be argued away. It is a consequence of counting, waiting patiently at the far end of a distance you will never cross. Somewhere the same lamp is on, and the person beneath it is just now deciding, wrongly and tenderly, that theirs is the only one. Thank you for still being here, this far into a strange and quiet idea. If you would like the next slow hour to begin on its own when this one ends, you can simply leave it to play, and it will find you. Nothing else is needed from you tonight. Let us keep going, slower now, and a little further out. Because everything we have said so far has leaned on one word we passed over rather lightly, the word endless. Space looks flat, and flat suggests it keeps going, and the whole argument for the twin needs it to keep going very far indeed. But it is fair to stop and ask why there should be so much of it in the first place. Why the universe did not simply come out small and stay that way. So the next movement is about where all that room came from, and the answer, oddly enough, is easiest to picture on a stove, in a pot of water just beginning to boil. Watch a pot of water in the last moments before it boils. For a while, nothing happens that you can see, only a faint trembling along the bottom. And then in one spot, a single bubble forms and rises, and somewhere else another, and the water between them keeps seething and stirring and making more. No single bubble is the whole event. The bubbles are the places where something has finished, where the water has turned to steam and broken free of the rest. The seething all around them is where it has not finished yet, where the change is still underway. Hold that picture loosely in your mind, the finished bubbles and the restless water between them, because we are going to need it before long, and it turns out to be one of the more useful ways anyone has ever found to think about the size of the universe. We have spent 2 movements treating that size as simply given, a stage that happens to be vast, and we leaned on its vastness to place your distant twin out at the far end of all that room. But bigness on this scale is not a thing to wave past as though it explained itself. A universe does not have to be enormous. It could, for all the laws seem to strictly require, have come out small and cramped and stayed that way. So the honest question, the one that keeps the whole argument from floating free, is where all this room actually came from. And the answer that cosmologists reach for is a short and violent stretch of growth right at the very beginning, in the first unimaginably small sliver of the first second. The idea is called inflation, and it was worked out in its modern form by the physicist Alan Guth at the start of the 1980s, though many hands have shaped and reshaped it since. What Guth proposed is that in the earliest instant, far earlier than the moment the fog cleared and the oldest light set out on its long journey to us, space did not simply expand in the steady, ordinary way we usually picture. It expanded exponentially, which is a different and much stranger kind of fast, and the difference is worth slowing right down for, because the word gets thrown around loosely in ordinary speech, and here it carries the entire weight of the movement. Steady growth adds the same amount in each equal stretch of time. A road being laid at a mile a day is longer by the same single mile each day. A plane and even lengthening you could predict far in advance. Exponential growth does something else entirely. It multiplies by the same factor in each equal stretch of time, so that the growth itself grows, and grows faster the larger the thing becomes. It is the arithmetic of compound interest, the quiet reason a modest sum left alone for long enough climbs far past anything the starting figure would ever have led you to expect. Think of a single penny that doubles every day. For most of the month it stays almost embarrassingly small. A penny, then 2, then 4, and you would be forgiven for losing interest entirely. But the doublings do all their dramatic work late and all at once, and by the end of the month that same penny has climbed into the millions, an amount no one watching the slow early days would ever have believed. Now take that same relentless doubling and apply it not to money, but to space itself, to the bare distances between points, and let it run for even the tiniest fraction of a second. A region far smaller than a single particle is carried out, in that one breath, to a size that dwarfs everything we will ever see. By the reckoning laid out in the standard cosmology texts, the scale of things grew during inflation by something on the order of 10 raised to the 30th, and all of it finished within about a trillionth of a second after the beginning. The mind cannot really hold a growth like that, and it does not need to. It only needs to hold the shape of it, a whisper of time, an almost incomprehensible swelling, and then the ordinary, far slower expansion that we still live inside quietly takes over. Now, this idea was not dreamed up in order to hand us copies of ourselves. That is worth saying plainly, because it is a large part of why so many careful people take inflation seriously, rather than treating it as a pleasant flight of fancy. It was invented to solve two stubborn and far more ordinary puzzles, and it manages to solve them both with a single stroke. The first is the very flatness we spent the last movement measuring. A universe left entirely to its own devices would not naturally sit balanced so precisely on the knife edge between curving open and curving closed. It would tend, as it aged, to drift one way or the other, toward folding shut or flying apart. But a short burst of exponential growth near the very start would iron almost any starting curve nearly smooth, the way a wrinkled sheet pulled hard from both ends comes flat under the tension. Cosmologists sometimes reach for a balloon to picture it. Imagine an ant standing on a small, tightly curved balloon, able to feel the curve beneath its feet. Now blow the balloon up to the size of a city, or a world, or a star. The ant has not moved a step, but the patch of rubber beneath it now looks and feels to the ant perfectly flat, because the curvature has been stretched out across a size the ant has no way to take in. Inflation does exactly this to space. Stretch a thing far enough, and its curvature all but vanishes from any local view. The idea predicts, in fact, that space should come out flat to very high precision, which is precisely what the ancient light told us when we finally drew our triangle across the sky. There is a quieter confirmation folded into this that is worth pausing on. Inflation does not only predict that space should look flat, it makes a sharper claim that the total amount of matter and energy in the universe should come out to a very particular value, the exact amount needed to keep space balanced on that flat edge, an amount cosmologists call the critical density. For a long stretch of years this looked like a genuine problem, because when astronomers added up all the matter they could find, the ordinary matter in stars and gas, and the far larger amount of unseen dark matter besides, the total came to only about a third of what flatness plainly demanded. The books would not balance. The missing 2/3 turned up, quite unexpectedly, in that same accelerating expansion we spoke of a moment ago, carried by dark energy, which supplies close to the remaining share. Add the matter, near a third, to the dark energy, near 2/3, and the total lands very close indeed to the critical value inflation had been asking for all along. The prediction and the ledger agree. It is the kind of quiet agreement that makes cosmologists trust an idea a little more, even one as wild as a whole universe unfolding from less than a speck in a sliver of a second. The second puzzle is the strange evenness of that same ancient light, and it is subtler, and once you see it, more haunting. The glow arrives at almost exactly the same temperature from every direction, from patches of sky so far apart that, in the ordinary telling, they could never once have touched. Light itself, in all the time since the beginning, has not had long enough to travel from one side to the other. Two such regions sit forever beyond each other's horizon, each unable to have sent so much as a single signal to the other across the entire history of the cosmos. And yet they share a temperature to a remarkably fine fraction, as though two rooms at opposite ends of a house that were never joined by any door, that shared no pipe and no open vent, had somehow settled on precisely the same warmth entirely on their own. Left unexplained, that quiet agreement is a genuine mystery. Inflation dissolves it gently. Before the great stretching, all of those far-flung patches were tucked up close together, near enough to mingle and trade warmth and come to a common temperature, and only afterward were they flung to the opposite ends of the sky, carried apart by the very expansion that had smoothed them. They match because they were once neighbors, in close and quiet contact, long before space grew so vast between them. The idea earns its keep on these two plain questions, and then, almost as an afterthought, it hands us an extraordinary one entirely for free. In the calm spirit of the night, it is worth stating plainly that inflation remains a hypothesis, not a settled fact. It is widely accepted among researchers because it explains so much so neatly with a single idea, but the conditions it describes are so extreme and belong to so early an instant that we cannot reproduce them in any laboratory or watch them directly through any telescope, and careful cosmologists will tell you frankly that we do not yet know for certain that it happened at all. We are following a very good idea toward its consequences tonight, not reciting a proven history. That distinction is a real one, and keeping it in view is part of what lets the whole picture rest lightly on you rather than press down. Here is where the boiling pot comes back to us. The field of energy thought to have driven that early stretching does not switch off cleanly everywhere at the very same instant. It settles, the way water finds its level, but the smallest quantum jitter keeps nudging it this way and that, and so it comes to rest in some patches while, in the patches between, the same restless jitter holds it up, and the stretching simply carries right on. Where the field settles, the growth ends, and ordinary time begins, and that patch cools into the kind of universe that can slowly gather itself into galaxies and stars, into worlds and warmth and, in time, into someone lying awake wondering about all of it. Where the field does not settle, the inflation continues, making more space, and out of that continuing froth, new patches keep dropping and settling and becoming universes of their own. each with its own beginning, its own long cooling, its own unrepeatable history. So there is never a last moment of inflation. There is always more of it happening somewhere in the seething between the finished bubbles, and always new bubbles forming and finishing and setting off on their own. The standard cosmology texts describe this ongoing version, sometimes called eternal inflation, as a process that is effectively without end, generating many separate inflating regions, each of them maturing into a universe. The boil does not run down like a kettle emptying towards silence. As best as the models can tell, it makes more than it spends, and it goes on making more without any stopping place we have ever been able to find. Notice what that does to the word universe. It quietly rearranges the whole picture beneath us. Everything we have been calling the universe, the entire sphere of galaxies out to our horizon, and all the unseen space beyond it that we argued must keep going, becomes in this larger view a single finished bubble. One cooled pocket in a vast and ongoing boil, not the pot, only one bubble in it, and there are others past all counting, some of them perhaps still forming even now, if the word now can be made to mean anything at all across that froth. Max Tegmark gathered this into the second and wider of his levels, and the most striking thing about these other pockets is that they need not resemble ours in the slightest. When a bubble cools and its energy finally settles, the fine details of how it settles can leave it with its own particular strengths for its forces and its own particular masses for its particles, drawn, in some accounts, from an enormous range of possible settings, more distinct possibilities than we have any real way to picture or to count. Most of those settings would make for a dead and silent place, a pocket where the forces are tuned so that atoms cannot hold together at all, where no star could ever kindle, where there is no chemistry and no warmth, and so nothing that could ever arrange itself into a mind to notice the silence. Only a thin sliver of all the possible pockets would come out tuned, as ours somehow is, to allow stable matter and long-burning stars and the slow, patient business of life. And that is not a cruelty and not a design. It is only a filter that we happen to sit on the living side of. We find ourselves in a pocket whose settings allow us, for the plain and almost circular reason, that a pocket whose settings forbid us has no one inside it to find themselves anywhere at all. Physicists have a modest name for that observation, the anthropic principle, and it does no more than remind us of something that is almost obvious once it is said out loud. Any window through which someone is looking out at the cosmos must, by the very fact that someone is there looking, be one of the windows that happens to open onto a place where looking is possible. The dark windows, the dead pockets, have no one at them to report the dark, which brings us softly back to the lamp. In that first and nearest level, the far lamp burned in a room identical to yours, only impossibly distant across a single endless space. Here in the second, wider level, most of the windows are dark in a far deeper way, whole pockets where a lamp could never light, because the very rules there forbid a flame. And yet, among the endless pockets that can hold a lamp, if there are endlessly many of those, each single one is itself a universe of the first kind, flat and roomy, and going on without end, with all the room it needs for its own quiet repetitions, its own distant copies of whoever happens to live there. The wider view does not thin the company out. It stacks it, level upon level, the same lamp forever finding new windows to burn in. Before we leave the wide view, there is one more thing to see about these rooms. What they are actually made of turns out to be humbling and strange in its own right. Cast your mind back to the ledger we balanced a little earlier, the one where the matter came to about a third of what flatness required and dark energy supplied the rest. It is worth pausing on that third, the matter, because most of it is a kind we have never once seen and cannot see, and we know it is there only by the pull it exerts. Start again with something familiar, the way the planets move around our own sun. There is a plain rule to it, one Kepler worked out long ago. The farther a planet lies from the sun, the more slowly it travels along its orbit, because the sun's grip weakens with distance. Mercury, close in, races around at nearly 50 kilometers every second. Neptune, far out in the cold, merely crawls at only about 5. The speed falls off with distance in a way that follows directly from where the mass sits, almost all of it gathered in the sun at the center. Measure how fast things orbit at different distances, and you are really weighing what lies inside their orbits. Now turn that same simple idea on a whole galaxy. A galaxy, like our own Milky Way, is a great turning wheel of stars and gas, and most of its light, most of its visible matter, is gathered toward the middle, thinning out toward the edges. So we should expect the outer stars and gas clouds to behave like Neptune, orbiting slowly because most of the mass is far inside them, with the speeds falling off the farther out we look. When astronomers actually measured it, tracking the orbital speed of hydrogen and other gas at greater and greater distances from the galaxy's center, they found nothing of the kind. The speeds did not fall off. Far out, well past where the light of the galaxy fades into darkness, the gas was still sweeping around just as fast as it did closer in. The curve that should have sloped gently downward instead ran flat, on and on, into regions where there was almost nothing left to see. There is only one honest way to read that. Something out there, far beyond the glowing edge of the galaxy, is gripping those outer clouds with its gravity, something heavy and spread wide and entirely dark. The stars we see turn out to be only the bright inner sliver of a far larger mass, a vast unseen halo of matter, reaching out well past the light, almost spherical, holding the whole spinning galaxy in its grip. We call it dark matter, and the name is really a confession, because it does no more than mark the fact that we cannot see the stuff at all. It gives off no light of any kind, no glow we have ever caught in any telescope on the ground or in space. We know it is there in the only way we can, by the steady pull of its gravity on the things that do shine. And this is not some quirk of our own galaxy. When astronomers turned to other galaxies, they found the same thing, the same outer regions orbiting too fast for the matter that shines, the same flat curves running out into the dark. When they weighed great clusters of galaxies, whole cities of them bound together, they found again that the visible matter came nowhere near enough to hold the cluster together, that most of the gripping mass was unseen. Wherever they looked and however they weighed it, the same answer came back. Most of the matter in the universe, most of the mass that shapes it and holds it together, does not shine. The ordinary matter we are made of, the matter of stars and planets and warm bodies in beds, turns out to be the small bright exception, a thin froth of light riding on a dark and heavy sea. The natural question is what the dark matter could be, and here the honest answer is that we do not yet know. Careful people have gone down the list of ordinary suspects and crossed them off one by one. It cannot simply be dim, failed stars or cold clouds, or vast numbers of small dark bodies drifting unseen, because a test exists for those. Any such object passing in front of a distant star would briefly bend and brighten its light, a small flicker astronomers have watched patiently for by staring at the stars of the Magellanic Clouds, and there are nowhere near enough of these flickers to account for all the missing mass. The leading thought now is that dark matter may be some kind of subatomic particle we have not yet caught, a sort of matter that feels gravity but otherwise slips through the ordinary world, almost without a trace, passing through you and the earth and the walls of the room, as though they were not there. If that is right, then a faint wind of it is drifting through this room as you lie here, felt by nothing, seen by nothing, and yet outweighing everything you can see. There is a second independent way we have of weighing the dark, and it comes from an old prediction of Einstein's, that gravity bends the path of light. A heavy thing in space does not only pull on other matter, it warps the very space that light travels through, so that light passing near a great mass is bent from its straight path, the way a lens bends a beam. Point a telescope at a massive cluster of galaxies, and the light of still more distant galaxies behind it, passing through on its way to us, comes out bent and smeared into arcs and rings and doubled images, the first such gravitational lens having been recognized in 1979. From the exact shape of that bending, astronomers can weigh the cluster doing the bending, and the answer agrees with the rest. The cluster is far heavier than everything in it that shines. Two entirely separate methods, the turning of galaxies and the bending of light, arrive at the same dark conclusion, which is a large part of why astronomers trust it. It is fitting that one of the great new observatories built to survey the sky and probe this mystery carries the name of Vera Rubin, an astronomer whose name has become bound up with the study of the unseen matter itself. Dark matter does more than hold the galaxies together. It very likely built them in the first place. Cast your mind back to those faint ripples frozen into the oldest light, the patches a whisker warmer or cooler than their neighbors. Those were the seeds, the first slight clumpings of matter in a nearly smooth young universe. Ordinary matter alone left to itself would have been too slow to gather into galaxies in the time the universe has had, still jostled and held apart as it was by the pressure and glare of the early heat. But dark matter, feeling only gravity and ignoring all that glare, could begin drawing itself together earlier and harder, pooling into a vast invisible scaffolding of dense knots and long threads. And into the deep gravity wells of that scaffolding, the ordinary matter later fell, gathering and cooling and lighting up into the galaxies we actually see. So the bright web of galaxies strung across the dark may be tracing out in light the shape of a darker web that was laid down first. The lamps in that picture were hung upon a scaffolding no one can see. So here is the quiet, humbling thing to carry away, softer than any fear. When we said the universe is, on the whole, the same kind of place wherever we look, full of the same matter, under the same rules, we were telling the truth, but not the whole of it. Most of that matter is dark. The rooms out there, the ones that repeat across the endless distances, and this very room you are lying in, are built mostly of a substance that gives off no light, and that we have never once seen, held together by the gravity of something we know only by its grip. The lit part of everything, the stars and the lamps and the faces, is the thin, bright edge of a much larger darkness, and even that darkness, it turns out, is simply more of the ordinary furniture of a universe that keeps being larger and stranger than its glowing surface ever lets on. Turn now to that thin, bright edge, the ordinary shining matter, the small fraction of everything we can actually see and touch. Even it has a strange and moving history. The stars and the planets and your own resting body are built of atoms, and those atoms were not simply always here, waiting. Almost every one of them was made, cooked into two great episodes separated by billions of years, and following where they came from turns out to be, very quietly, the story of where you came from. The first episode happened in the opening minutes of everything, and it was brief. In the first movement, we watched the young universe as a hot, dense fog of light and particles. It was also, for a few short minutes, hot and dense enough to act as a single vast furnace, fusing the simplest particles into slightly heavier ones, the way the core of a star does. But this cosmic furnace had almost no time to work in. The universe was expanding and cooling with every passing second, and the window in which fusion was possible slammed shut almost as soon as it opened. Between roughly 3 and 4 minutes after the beginning, particles were fusing into deuterium, a heavier form of hydrogen, and much of that deuterium was fusing into helium. And then, by about 4 minutes in, it was already over. The universe had thinned and cooled too far, and the building stopped. In those few minutes, the cosmos made a great deal of hydrogen, the simplest element of all, and a good quantity of helium, the next simplest, coming out to roughly 3/4 hydrogen and 1/4 helium by weight, along with a faint trace of lithium. And there it halted. It made almost nothing heavier. No carbon, no oxygen, no nitrogen, no iron. None of the richer elements that a rocky world or a living body would ever need. That the Big Bang should make so much helium, and just about the amount we actually find, is one of the quiet triumphs of the whole picture, because there is far too much helium in the universe to be explained by stars alone. Even the oldest stars we can find, and the most distant galaxies, are already laced with it, as though it had been there from the very start, which, on this account, it was. But the same short window that made the helium also explains poverty. The early universe was a place of only the two lightest gases and little else, and a universe of nothing but hydrogen and helium is a universe with no way to build a planet, or a stone, or a hand. There is a delicate thread left over from those minutes that is worth pausing on, because it reaches back to the darkness we were just discussing. That trace of deuterium, the heavier hydrogen made in the first 4 minutes, is fragile, and how much of it survived depends very sensitively on how densely the ordinary particles were packed at the time. Measure how much deuterium the universe still holds today, and you can read backward to how much ordinary matter there is, the matter made of protons and neutrons, the matter that can shine. And the answer that comes back is small, far too small to be all the matter the galaxies plainly need to hold themselves together. So the faint deuterium left from the first minutes turns out to be one more independent finger pointing at the same conclusion, that most of the matter in the universe is not the ordinary shining kind at all. Two numbers taken from utterly different eras, the turning of galaxies now and the cooking of light elements then, quietly agree. So if the heavier elements were not made in the beginning, where did they come from? The answer is that they were made and are still being made inside the stars. A star is a slow and patient furnace. Across its long life it fuses the light elements into heavier ones in its core, hydrogen into helium, and then, as it ages, helium into carbon and oxygen. And in the most massive stars, the building climbs on, step by step, forging heavier and heavier elements up toward iron. The elements heavier still, past iron, the silver and the gold and the rest, are thought to be forged in the tremendous conditions of a dying star, when the largest stars reach the end of their lives and collapse and blow themselves apart. What matters for us is what happens next, when a star dies, gently as a fading ember, or violently as an explosion. It does not keep its riches to itself. It scatters them, casting the heavier elements it has spent a lifetime making back out into the thin gas and dust that drift between the stars, enriching that reservoir, seeding it. And from that enriched reservoir, new stars are born, a little richer in the heavy elements than the ones before them, and around some of those new stars the scattered heavy elements gather into rocky worlds. Think of it as an inheritance, passed down and added to across many generations. The very first stars had only the hydrogen and helium of the beginning to work with, and could leave only a modest legacy. But each generation that lived and died left the next a little more to build with, a little more carbon and oxygen and iron mixed into the raw material until, after billions of years and many generations of stars living and dying and enriching the mix, there was finally enough of the heavier elements gathered in one place to make a star like our sun, with rocky planets around it, and on one of those planets, atoms complex enough to gather themselves in time into something that could lie awake and wonder where it all came from. Which means the ending of this small thread is closer to you than any of the vast distances we have crossed tonight. The carbon in every cell of you, the oxygen you are breathing slowly in and out as you rest, the iron carried in your blood, the calcium laid down in your bones, none of it was made on the earth, and none of it was here at the beginning. Every heavier atom in your body was forged inside a star that lived and died before the sun was ever born, and was scattered across space in that star's ending, and drifted for ages, and was gathered up at last into the cloud that became the sun and the earth, and eventually you. We are, in the plainest and most literal sense, made of the ashes of dead stars, ordinary matter recycled through generation after generation of them. It is not a metaphor. It is where the atoms came from. So the rooms that repeat across the dark are not only the same shape, they are cooked from the same short list of ingredients, forged in the same kinds of furnaces. The light elements from the first few minutes, and the heavier ones from the long lives and quiet deaths of stars, everywhere, under the same unchanging rules. It is one more way the far copies are kin to you, and a deeper way than mere resemblance, because they share not only your arrangement, but your very substance, the same long inheritance of a whole universe slowly learning, across billions of years, how to gather stray starlight into a thing that could wake in the night and be glad of it. Every distant version of you is lit, quite literally, by the ashes of stars that died, so that a lamp and a hand to switch it on could one day exist at all. Before we turn back toward the small warm room and the coin on the nightstand, let us come home for a moment, out of all these vast abstractions, to the actual place we live. Because we have been speaking of endless space and countless pockets and copies past all counting, and it is easy to forget that all of this is happening somewhere, that you have an address in it, a real and particular corner of the whole. Think of how it feels to find your own house in a photograph taken from very high up. First, there is only the curve of a coastline, or the sprawl of a whole region, too large to hold. Then you find the city, and then the neighborhood, and then, with a small quiet jolt, the roof you sleep under, one among thousands, no different to the camera than any other, and yet the only one that is yours. Let us do that with the sky. The stars you can see on a clear night, every single one your eye can pick out. belong to one great island of stars that we call the Milky Way, our home galaxy. It is a vast turning wheel, a disk of hundreds of billions of stars, with a bar of them laid across its glowing middle, and it is so wide that light itself, for all its speed, takes something like 100,000 years to cross from one edge to the other. On a dark night, far from any town, you can see it directly, the faint band of milky light arching overhead. That soft band is the combined glow of countless stars in the flat disk of our galaxy, seen edge-on from the inside, because we live within the wheel and are looking out through it. And where in all that are we? The sun sits somewhat less than 30,000 light-years out from the center, roughly partway toward the edge, in a spot the astronomers describe, almost tenderly, as having nothing much to distinguish it. We are near the inner edge of a modest spiral arm, a minor one, not even one of the galaxy's grand sweeping features, but a smaller spur between them. Our whole solar system, the sun and the earth and every place any human being has ever stood, drifts there in an unremarkable neighborhood of an ordinary galaxy, slowly circling that distant center, one long unhurried orbit that takes so much time to complete that the whole of human history amounts to less than a single step of it. We cannot even see the center we are orbiting. It lies off in the direction of the constellation Sagittarius, and between us and it hang such thick clouds of dust that our view is blocked, the way the far end of a valley vanishes into haze. We circle a heart we cannot look upon, and around the whole bright wheel, reaching far beyond the last visible star, is that vast unseen halo of dark matter we spoke of, holding the turning galaxy together, an invisible sphere of the unlit substance within which our whole lit home is cradled. The stars are the glittering part, but they are the minority. Our galaxy is mostly the dark thing we cannot see, with the light threaded faintly through the middle of it. Now pull the camera back once more, gently, the way it drew back from the roof at the very start of the night. Our great galaxy, 100,000 light-years wide and holding its hundreds of billions of stars, is itself only one island among many. Not far from us, as these things are measured, lies another great spiral, Andromeda, a little more than 2 million light-years off, and our two galaxies are the largest members of a modest gathering of more than 50 galaxies that all drift along together, held loosely by their gravity, which astronomers call, with a kind of homely warmth, the local group. And the local group in turn is only one small cluster among the clusters, gathered into still larger structures, the great web of galaxies strung across the dark that we glimpsed earlier. Galaxy upon galaxy, cluster upon cluster, out to the edge of the visible and, if the night has been right, far beyond it. Which brings the far lamp home in a way it has not been before. When we picture that endless dark city of identical lit windows, we can now see what each window truly is. It is not merely another room. It is another whole galaxy, or a room within one, an island of hundreds of billions of stars very like this one, turning slowly in its own dark halo, with its own faint band of milky light arching over its own version of you, who is looking up through their own dusty spiral arm at their own unremarkable sky, and thinking, as you might be thinking now, that surely this particular place, this one ordinary neighborhood in one ordinary galaxy, must be the only one where anyone is awake and wondering. The address is real, the room has a location, and the astonishing thing the whole night has been saying is only that the address, however precise, however truly and particularly yours, is not unique. It is filled in again, somewhere out past the dust and the dark, in a hand exactly like the one resting near you now. But notice that all of this has kept your copies at a comfortable remove. Whole universes away, sealed inside other bubbles of the boil, or out past a distance in our own space that no light will ever cross. It would be fair, lying here in the one room you can actually feel around you, to decide that whatever is happening out there in the enormous elsewhere, this place at least is singular. One quiet room with a single one of you resting in it. So the next movement brings the idea close, closer than any distance. It comes down out of the far pockets and the far reaches and settles onto the coin you might leave on your own nightstand, and into the ordinary moment, every single night, when you cross from awake into sleep and never once catch yourself doing it. Everything until now has kept your copies at a safe remove. Out past a distance no light will ever finish crossing, or sealed away inside other bubbles of the endless boil. It would be reasonable, lying here in the one room you can actually feel around you, to hold on to the thought that whatever is happening in all that enormous elsewhere, this place at least is singular. One quiet room with a single one of you resting inside it. The last widening of the idea takes even that away, and it manages this not by reaching outward, but by looking closely, closer than any telescope has ever looked, down into the smallest workings of matter, into the very grain of things. Quantum theory is the most exactingly tested description we have ever built of how the small world behaves. It is not a loose sketch or a promising guess that we are still deciding whether to trust. When physicists calculate the tiny magnetism carried by a single electron, a quantity they call its magnetic moment, and then measure that same magnetism in the laboratory, the prediction and the measurement agree to better than 1 part in a trillion. It is often described as the most precise agreement between a theory and an experiment anywhere in all of science, and it is hard to find anything in ordinary life to set beside it. Picture measuring the distance across an entire continent and coming up wrong, at the very end of it, by less than the width of a single human hair. That is roughly the fineness we are speaking of. That is the level of trust this theory has slowly, stubbornly earned. And this most trustworthy of all our theories says something genuinely peculiar about what a thing even is before anyone looks at it. It does not describe a particle as sitting quietly in one definite place, waiting for your glance to confirm where it was all along. It describes it instead as a blend of possibilities, each one carrying its own share, all of them present together at once, and all of them evolving side by side in a smooth and lawful way. The electron is not simply here, or simply there, but a weighted mingling of here and there, spread across its options the way a chord is spread across several notes, rather than sounded as one. If that sounds like a mere trick of arithmetic, a bookkeeping convenience, there is an old and careful experiment that suggests otherwise. Send single particles, one at a time, with long pauses between them, toward a barrier with 2 narrow openings in it, and let them land on a screen behind. You might expect each particle to go through one opening or the other, and to pile up in 2 simple bands. That is not what happens. Over many particles, sent one lonely at a time, the landing spots build up into a pattern of many stripes, the telltale ripple of something that passed through both openings at once and met itself on the far side, even though each particle was sent entirely alone. The single particle behaves on its way, as though it explored every path available to it, and only on arrival does it commit to a single point. The blend of possibilities is not a way of hiding our ignorance about where the particle really was. As far as the experiment can tell, the blend is the truth of the matter, right up until the moment of contact. And then, when the particle meets the wider world, when it is measured or bumped or simply tangled up with something large and warm, a single outcome seems to step forward out of the blend, and all the others seem to quietly fall away, as though the chord had suddenly collapsed to one clean note. The strange part, the part that a young physicist named Hugh Everett noticed in the 1950s and would not let himself stop noticing, is that the falling away is nowhere in mathematics. The equations describe the blend of possibilities evolving smoothly and predictably, and they never once contain a step where the blend jumps to a single answer and throws the others out. That jump was added by hand. It was written into the practice of physics by careful people who needed the theory to match the single definite outcomes they actually saw in their instruments, and as a working recipe, it succeeds beautifully, day in and day out. But it sits inside the theory like a seam stitched in from outside, a rule with no real home in the equations themselves. Everett, in his doctoral work at Princeton, published in 1957 under the quiet title of A Relative State Formulation of Quantum Mechanics, proposed something disarmingly simple. He proposed that we take the seam out, keep only the equations we already trust and lean on every day. Let the blend of possibilities be the whole of the truth, always evolving, never collapsing down to one. The vivid name this picture usually carries now, the many worlds interpretation, came later and from other hands. Everett himself gave it only the plainer title of a relative state formulation, and he wrote less about worlds than about equations taken honestly at their word. His idea was largely set aside for years, thought too strange to be useful, before it was taken up again and argued over seriously by a later generation, which is roughly where the argument still stands. And if you do take the seam out, the possibilities do not vanish when you look. They stop overlapping. The act of measuring, the looking, the ordinary contact of a small delicate system with the large, warm, cluttered world around it, tangles the outcomes into that world so thoroughly and so quickly that they can no longer reach across to one another, can no longer blend or interfere or send any signal between themselves. Physicists call that process decoherence, and once it has happened, each outcome simply carries on as its own branch of reality, complete and fully furnished and entirely unaware of the others running alongside it. The coin that could have landed two ways lands both, in branches that from that instant forward can never touch again. And you, standing over the coin, watching to see how it fell, become two versions, each one seeing a single face, each one holding a whole and seamless memory of the one ordinary evening they are certain they spent. This is also quietly the reason the everyday world looks as solid and single as it does, the reason you have never once watched a coin blur into both faces at your kitchen table. The delicate overlap that lets possibilities interfere survives only in careful isolation, in the shielded stillness of an experiment built to protect it. Anything large and warm, a coin, a cat, a sleeping person, is touched by so much of the surrounding world at every instant, jostled by countless stray flecks of light and air, that the overlap is torn apart almost the moment it forms. Decoherence is swift and thorough for big things, so the branching is entirely real on this reading, and yet it is always already hidden by the time anything your size could ever hope to notice it, which is exactly why the single seamless world is the only one you have ever been shown. Here is where the night itself becomes the gentlest teacher, because you already know, in your own body, how a splitting can leave behind no seam at all. You have never once felt yourself fall asleep, not on any night of your life. Every night you cross from waking into sleep, and the crossing keeps no record of itself. There is the lit room and your thoughts wandering loose and slow, and then there is morning, and in between there is nothing you can point to, no line, no threshold, no single moment you could ever mark and say, there, that is where I went. There is a reason for that, and it is a real one. As you fall asleep, the brain shifts into the slow, synchronized rhythms of early sleep, and the systems that lay down new memories that would ordinarily record the passing moment, so you could recall it later, quiet down and stop writing. The threshold is not forgotten so much as never encoded in the first place, so there is simply no memory of it to find. And yet the night feels afterward like one unbroken thing, whole and continuous, even though for hours you were, in every sense that matters, gone. Branching, if Everett had it right, is a little like that crossing. There is no jolt when it happens, no sense of tearing, no inner announcement that reality has just gone two ways. Each version simply finds itself already on its own side, holding a past that feels perfectly seamless, as sure as you are sure at this very moment that only one thing is happening in this room. And that is why this level, out of all of them, comes to rest the closest to you. It asks for no endless space and no eternal boil. It asks only that the equations we already lean on, the ones tested to that trillionth part, mean exactly what they say, all the way down, with no seam sewn in at the very end to tidy the picture. It is only fair to say, in the same honest spirit as before, that this is one way of reading the theory and not the only one. Everett's picture, with its unfelt branches, is a serious and much discussed interpretation, but there are others that thoughtful physicists hold to just as carefully, some that keep a version of the collapse, some that add a little to the equations rather than take a little away. The disagreement among them is real and still unsettled, and it runs deep, but it is a disagreement about how to understand mathematics, rather than about the mathematics itself, and rather than about what any experiment will show. On the numbers everyone agrees, and the numbers are what have been tested to that trillionth part. So hold the branches lightly, as one honest reading of a theory whose predictions are beyond doubt, but whose deepest meaning is still gently in question. If they do, then the nearest other you is not waiting out past some unthinkable distance in the dark. It is here, in this room, one branch over, having just chosen the word you did not choose. Turn toward the thought you did not turn toward, reaching for a lamp in a room laid out exactly like this one. It is already as far beyond your reach as the most distant copy in the deepest elsewhere, because branches that have once parted can no more meet again than two regions of space flung past each other's horizons. And yet it is close in a way that none of the others were, close enough that you might have brushed against it only a moment ago, in the last small thing that could have gone either way. Now, there is a piece of this that matters especially for the version of you who still has choices left to make. So let it settle softly, rather than slip past. Not all of these branches carry the same weight. The theory does not hand out its possibilities evenly, as though every outcome were equally likely simply because it happens somewhere. It assigns each possibility a share, more weight to some and less to others, and those weights turn out to be exactly the odds you have always used, without ever thinking about it, whenever you reasoned about chance in ordinary life. The likely things stay likely, the unlikely things stay rare. So, a careful choice, made with attention and with care, still tilts the branches toward the outcome you were reaching for, just as it always seemed to. Working out precisely why those weights should behave like everyday odds, inside a picture where every outcome genuinely occurs, is a real and unfinished piece of the theory, one that thoughtful people are still turning over and have not fully closed. But the plain shape of the answer is a kind one. Your choices are not hollowed out by all this branching. The branch you tend, by your attention and your effort and your care, is the branch you will find yourself living in, and the versions who chose otherwise are living theirs, no less real than you and no more, each of them equally certain that their single quiet evening is the only one there is. So the coin resting on the nightstand is a small door, and both of the rooms behind it are furnished and warm, and in each of them a version of you is settling in for the night, drawing the blanket up, reaching for the switch. Somewhere, one branch over, closer than the far side of this room, and every bit as unreachable, the same lamp is on. But an idea this generous with copies should make us a little careful, and not only comforted, because a universe willing to make almost anything, given enough room and time, will also be willing to make things that ought to give us pause. So before we let the night carry us gently downward, we owe the whole picture one honest counterweight, and it arrives fittingly in the quiet shape of a bookkeeper sitting down to check a ledger she does not entirely trust. The idea we have been following all night is generous almost past bearing. Give the universe room enough and time enough, it keeps saying, and anything that can possibly be assembled will be assembled somewhere sooner or later, and then assembled again. That very generosity is what handed us the far twin, lying in an identical room, and the near branch resting only one step to the side. Honesty asks that we follow the same rule into a less comfortable corner, because a rule does not get to apply only where it happens to please us. If the universe will build your distant double simply because it can, then we are obliged to ask what else it will build for exactly the same reason. The thread to pull was left for us by Ludwig Boltzmann, a physicist working in the 1800s on heat and disorder, on why warm things cool and why the world tends, left to itself, toward a comfortable mess. What Boltzmann saw and set down in the language of probability is that order is not forbidden, only rare. It is simply outnumbered. He understood disorder as a matter of counting, and even wrote down the relation that ties the two together, a small equation now carved onto his gravestone in Vienna, which says, in effect, that the disorder of a state grows with the number of distinct ways its pieces could be arranged and still look the same. There are only a handful of ways for a thing to be neat and a staggering number of ways for it to be jumbled. So, left to chance, a thing drifts toward the jumble for no deeper reason than that the jumble has so much more room in it, so many more arrangements that count as untidy than arrangements that count as tidy. A drop of ink loosed in a glass of water spreads and pales to an even grey, and never, in any kitchen anyone has ever watched, gathers itself back into a single dark drop, not because the gathering is against the law, but because there is only one way to be that neat drop and countless ways to be the grey. And yet, Boltzmann understood, given time past all imagining, even the wildly unlikely tidy arrangement could in principle assemble itself once again by sheer chance. Rare is not the same thing as never. It only feels that way across any stretch of time a person could ever live through. there is something else hidden inside that simple observation, something that quietly shapes the whole of your experience without your ever noticing it. This one-way drift from the rare and tidy toward the common and jumbled is very close to what gives time itself a direction. The reason you remember the past and never the future, the reason a drop cup shatters and never gathers itself back whole onto the table, the reason the ink spreads and never regathers, is that the universe began in an extraordinarily ordered, low disorder state and has been gently unwinding from it ever since. Physicists call the steady growth of disorder the second law, and it is less a stern rule handed down from above than a simple counting of the odds, playing itself out across everything, everywhere, all the time. The past is only the more ordered end of that long unwinding. The future is the jumbled end, and we ride the quiet current between them, always, in the one direction the counting allows. That unwinding has a direction it is heading in, and it is worth following all the way to its far end, because that is where the next idea quietly lives. Far in the future, the stars will have spent their fuel and gone dark one by one, and the accelerating expansion we met earlier, that faint, steady pressure carrying everything apart faster and faster, will have thinned the contents of space out further still, drawing the galaxies beyond one another's reach, and leaving vast cold stretches of almost nothing between the last cooling embers. Carry your thoughts all the way into that immense, dilute, patient future, colder and emptier than any night you could ever picture. There, you arrive at an idea that cosmologists take seriously rather than wave away, uncomfortable as it plainly is. In that enormous quiet, faint, random fluctuations would still stir the thin remains of things, and once, in an unfathomable while, across stretches of time that make the current age of the universe look like a single held breath, a fluctuation could in principle gather enough order in one place to assemble something as intricate as a single conscious mind. A mind complete with a whole set of memories it never actually lived, a false past sewn into it in the very instant of its making, convinced it has a childhood behind it, convinced it is sitting in a room somewhere, remembering exactly how it got there, and lasting perhaps a single moment before it dissolves back into the dark it came from. Physicists gave this strange guest a name, the Boltzmann brain, and the unsettling question it raises is not really whether such a thing could ever form. Across enough emptiness and enough time, the arithmetic says it could. The question is whether, in certain models of the universe, it would form so often, over such vast reaches of empty time, that a typical mind in that universe would be one of these lonely flickers rather than one of us. And if that were somehow so, the thought runs, then how could you ever be truly certain that you were not one yourself? This very room and these very memories invented a heartbeat ago and gone a heartbeat from now. Here is where the calm comes back, and it comes back through the bookkeeper. Picture someone careful going slowly down a long ledger, and she does not trust a total simply because the arithmetic ran cleanly to the bottom of the page. She watches instead for the figure that is a little too convenient, the sum that comes out suspiciously round, the entry that would mean something plainly absurd if she took it at face value. And when she finds one, she does not accept it as news about the world. She reads it as a sign that something has gone wrong higher up the column, and she goes back to check the work. Cosmologists do exactly this with their own theories. When a model of the universe predicts that most of the minds within it ought to be lonely flickers with invented pasts, they do not read that as a chilling fact about you and me. They read it as an error flag on the model itself. because a theory that makes most observers into brief hallucinations has quietly sawn through the branch it was sitting on. It can no longer trust the very observations and memories it was built, in the first place, to explain. And worse, it cannot even trust the reasoning and the evidence that led anyone to propose it. Since that reasoning was done with a mind and recorded in a memory, the theory has just declared most likely to be a fluke. A theory that undercuts its own evidence in this way is a theory to send back for repair, not a verdict to lie awake beneath. And the evidence, when the bookkeeper actually checks it, points the reassuring way. We do not find ourselves as a single flicker adrift in an empty void, holding one disconnected and dissolving instant. We find ourselves inside a large, coherent, orderly universe, with a sky full of consistent history, with a past that hangs together, and a world that stays reliably where we left it whenever we look again. That deep coherence is itself the reason to think we are the ordinary kind of mind, the kind that was slowly grown over billions of years inside a low disorder cosmos, rather than the kind briefly and improbably guessed into being out of the cold. The very orderliness of everything around you, the fact that the room is still here and still makes sense, is the quiet evidence against your being a fluke. A lonely flicker would have no reason to find a world that is carefully stitched together. You do, every single morning. There is a second honest doubt, quieter and more technical than the first, and it is worth naming aloud gently, because it is what keeps the whole night from hardening into a false certainty. When everything happens and happens endlessly, and you then try to ask how likely any particular thing is, you run straight into a plain and ancient difficulty. Endless collections are genuinely hard to compare. Ask whether there are more even numbers or more whole numbers altogether, and you can answer it two perfectly honest ways that flatly disagree. In one way, there are clearly fewer evens, since the evens are only every other number, plainly half of the whole. In another way, there are exactly as many, since the mathematician Georg Cantor showed, more than a century ago, that you compare each whole number with its own double and never run out of either, matching them off 1 to 1 forever, with none left over on either side. Both answers are correct. Which one you get depends entirely on the tool you reach for before you even begin to count, and the counting itself never settles it. That same trouble falls across the multiverse like a long shadow. If there are endlessly many copies of you who chose one way, and endlessly many who chose the other, then asking which choice is the more common, or how likely your own particular situation really is, needs a way of weighing infinities against one another that we do not yet fully possess. Cosmologists call this the measure problem, and they keep it firmly among their open questions rather than among their settled results. It is not a small footnote tucked away at the end. It is an honest and acknowledged gap sitting right in the middle of the picture, named plainly by the very people who know mathematics best. And here is the thing worth carrying down towards sleep. That open gap, far from spoiling the picture, is the most reassuring part of it. The far twin, the boiling pockets, the branch resting one step over, none of these is being sold to you tonight as proven furniture of the world, bolted down and beyond question. They are the honest consequences of our best current models, offered with the seams still showing, and the doubts kept plainly in view, and the arithmetic still, right now, being patiently checked by careful people who would very much like to find the errors. A picture that openly admits what it hasn't yet managed to count is a picture you can rest beside without being asked to believe too much, or to hold on to anything too tightly. It does not demand your certainty. It only offers you its company and its honesty about how much it still does not know. But there is one more edge to all of this, the furthest and the quietest of them, and it asks you to hold on less tightly still, not more. So let the argument open its hand here and drift out past even the physics toward a strange and gentle idea. The idea that the mathematics we have been trusting all night may not so much describe the far rooms as, in some sense, no one is quite sure how to test, simply be them. There is one rung further out than all the others, and we will only rest a hand on it lightly, because it is the most speculative thing anyone in this whole story has said, and the man who said it would be the very first to tell you so. When physicists describe our world at its deepest level, down beneath the particles and the fields and the forces, what they find themselves writing, in the end, is mathematics. And the further down they go, the harder it becomes to point to any separate stuff underneath the equations, any solid substance that the mathematics is merely a description of. There seems, the closer anyone looks, to be only the structure itself, only the relationships and the patterns and the precise way each thing stands to every other thing, all the way down, with no final flaw of ordinary matter waiting quietly at the bottom to be the thing the mathematics is about. You can feel the pull of that observation even without the grand conclusion Tegmark draws from it. Ask a physicist what an electron truly is, and everything they can honestly tell you turns out to be relational. A patient list of how it answers to forces, how much it weighs, what charge it carries, how it behaves when it meets other things. Each answer is a number, or a rule, or a relationship to something else. Nowhere in the whole careful description is there a separate account of what the electron is made of underneath all its behaving, some quiet inner stuff that the numbers are merely painted onto. The behavior, the relations, the structure seem to be the entire story, and the long search for a substance beneath them keeps coming back empty-handed. That much is a plain and widely shared observation. What Tegmark then does with it is the daring part, and the part to hold most loosely of all. Max Tegmark took that quiet observation and asked a question most people would never dare to say aloud. If our deepest and truest description of reality turns out to be a particular piece of mathematics, he wondered, then why should our particular mathematics be the only one that gets to be real? And his answer, offered gently as a serious proposal, and never once as a certainty, was that perhaps it is not the only one. Perhaps every self-consistent mathematical structure exists in just as full and solid a sense as ours does, each one its own complete and self-contained reality, and we happen to find ourselves inside this particular structure only because it is among the ones rich enough and stable enough to hold together something that can sit up inside it and wonder about the whole arrangement. He called it the fourth and outermost of his levels, and it is a genuine reach, further out than all the others by a very long way. Many thoughtful people find it a step too far, and they say so plainly. Too hard to test, they argue, too far removed from anything a telescope or a laboratory could ever hope to check, too close to pure philosophy to comfortably wear the name of physics at all. And they may very well be right about that. The idea leaves the question honestly open, sitting out there at the far edge where our maps run thin and finally give out, and there is no need at all for you to decide it tonight, or indeed ever. We touch it not to talk you into believing it, but because it marks the outermost edge of the very same simple road we have been walking together all night. The road that began with nothing grander than a triangle drawn across the oldest light in the sky, and then kept quietly widening, one plain and patient step after another. And out here at the far end of it, the copies of you have long since passed beyond counting, in every sense the word can possibly hold. So let the whole of the night gather now, softly, while your eyes do whatever it is they would like to do. Think back over the distances we crossed to get here, because they arrange themselves, at the end, into something almost gentle. First there was the single endless space, flat as the ancient light revealed it, and out across it, at a distance no light will ever finish, a version of you lying just like this in a room, laid out just like this one, certain in their bones that they are the only one. Then the space itself became just one cooled bubble in an endless boil, and among the other bubbles, in one that happened to settle into the same gentle rules as ours, another version was doing the very same thing. Then we looked not outward but downward, into the grain of matter, and found the nearest one of all, one branch to the side, closer than the far wall of this room, and every bit as impossible to reach, having only a moment ago chosen the word you let go of. And now, at the outermost edge, past even the branches, they scatter into more structures than counting was ever built to hold. In every single one of them, the same past is folded quietly away, the same long history, the same set of memories each of them is entirely certain belongs to them and to no one else alive. In every one of them, the same small warm circle of lamplight, and every one of them is wrong in the very same tender way, wrong to believe the light is theirs and theirs alone, and every one of them is company that you will never once meet and never once lose. Here is the single thing this whole vast picture cannot reach, and it is worth carrying down with you into sleep, because it is the quiet gift the fear was hiding all along. Every copy of you, at every level, shares your past. Not one of them shares your next choice. The far twin was settled and fixed in the very moment they came to match you, an exact echo of everything you have already been and already done. All of it finished, all of it lying behind them. But the small thing that you are going to decide next, the word you have not yet said, the turning you have not yet made, the kindness or the patience or the care you have not yet spent, has not yet happened in any of them. And when you finally make it, you make it here first, in the one and only room where it is still unmade. The mathematics that can copy an entire life, atom for careful atom and memory for memory, can only ever copy what is already finished and done. What is not yet chosen stays, for this one held breath, only and entirely yours. So the fear the ideas seem to be carrying all this time turns out, when you finally hold it up quietly to the light, to be its exact opposite. You are not being told that you are one of countless interchangeable strangers scattered thinly through an indifferent dark. You are being told that you are never quite as alone as the deep quiet of the room can sometimes make you feel. That small circle of light you are lying inside right now is only one of an endless and gentle company of lights, each one tended by someone as real and as certain and as singular as you feel yourself to be. And that the one thing which has always and only been yours, the next small choice, is still, even now, even this late into the night, waiting patiently on you, and on no one else in all of it. There is nothing here to hold on to, and nothing left to solve. Let the far lamps go on burning where they are, out past every distance, in every pocket, one branch over, none of them reachable, and none of them ever truly lost. Let yours go soft now. Somewhere the same lamp is on, and it is only here, only now, going gently and willingly out. Rest here as long as you like. When you are ready, or when you are already half gone, there is just a little more, and then the quiet. Tonight we followed one plain thread, and the thread never once asked us to believe in anything strange. It began with a triangle drawn across the oldest light in the sky, that faint, even glow that Penzias and Wilson first stumbled onto as a hiss they could not clean away, and that Kobe later measured so carefully from above the muffle of the air. And it ended out at the very edge of what anyone has dared to call real. All the way along it, the thread asked for only 3 quiet and ordinary things. That space keeps going, the way its flatness gently suggests that it does, that it stays, on the larger scale, the same kind of place we already see in every direction we turn to look. And that the equations we already trust, the ones tested to finer than a trillionth part, mean exactly what they say, all the way down, with nothing added in by hand at the very end. From those 3 plain requests, and from nothing more exotic than those, came a distant twin lying in a room like this one, and a boiling field of pocket universes, each with its own quiet rules, and a version of you resting one branch to the side. Max Tegmark gathered all of it into 4 widening views, each one nested inside the next like rooms opening onto larger rooms. The nearest, a copy of you somewhere out across a single endless space. The next, a copy in another cooled pocket of the endless boil. The nearer one still, a copy one branch over in the grain of matter itself, and the furthest, out past all counting, in structures we can barely find the words for. He puts an actual number to the distance to the very nearest you, and whether the outermost of his levels turns out to be true, or only a beautiful reach too far, the nearest of them asks for almost nothing at all, and gives back, in return, a whole sky full of quiet company. It is worth holding gently as you drift, which parts of tonight were solid ground, and which were far away. That space is flat we have actually measured, in the angles of the oldest light across the sky, that it has been expanding for close to 14 billion years, and is expanding faster now than it once was, we have read from exploding stars in distant galaxies. That the small world is a blend of possibilities, we have tested past a trillionth part. Those are not guesses. The twins and the branches and the outermost structures are only where those solid, checkable measurements are carried, one careful step at a time, toward their stranger conclusions, and the further out the road went, the more lightly it was all meant to be held. The ground beneath the near end of the night is as firm as almost anything in science. Only the far end ever asked for faith, and even then it asked for very little. It is worth remembering, as the night settles, that every step of this was found by someone who was themselves just a person wandering in the dark. Eratosthenes with his shadow and his well, Boltzmann with his patient counting of the ways a thing can be, Everett, young and stubborn, refusing to look away from a seam no one else thought to question, Parfit, who followed the hardest questions about the self all the way down and came back out of them lighter than he went in. They were not so different from you lying here now, turning a large idea over in a quiet room. The company that night keeps promising you includes them too. If any of it stays with you, and you would like the next slow hour to begin on its own when this one fades, you can simply leave it to play, and it will be there waiting for you. There is another already resting in the queue, and it will begin soft, the way this one did, And if this is a place you would like to find your way back to on the nights when your mind will not quite settle, following along quietly is what helps the next person who lies awake wondering. These same things find their way here too. That is the whole of the asking, and it can wait easily until morning. There is nothing at all you need to do tonight. For now, there is nothing left to understand, and nothing left to hold. The far twins will go on being far, and go on being company, whether or not either of you ever knows the other is there. Your next choice is still yours, still unmade, still waiting with all the patience in the world until you wake and spend it. And the lamp, the one we started on, the single one that is only ever yours, is going gently out. Somewhere the same lamp is on. Sleep well.